Hello everyone, good afternoon, and welcome to COM 112 lecture. Today, students, we're going to be treating the topic on NOR and NAND implementation. And I hope by now you've not forgotten the logic gates we've treated so far. So far we've treated 3 logic gates, which is the OR gate, AND gate, and NOT gate. So now we are going to be treating what I would like to refer to as composite gates. That means these are gates that are made up of combining 2 different gates together, and the first one is NOR gate and NAND gate. So moving on, NOR gate. NOR gate comes from the combination of 2 gates, which are the NOT gate and the OR gate. So breaking it down, it actually means not OR gate. So combining the beginning of the first gate, that is letter N, and the OR gate gives us NOR gate. Once again, it fully means not OR gate. So it means when you have your OR gate, this is the drawing for the OR gate, and then we have the little circle attached to it, which is the NOT gate. It's negating whatever has entered the OR gate. This little circle here has negated it, that is, has changed it to the opposite. So if we have, say for instance, we have 2 inputs, A and B, into this OR gate, meaning A or B. Okay, sorry for that. Meaning A or B, the output coming out of the NOR gate of the NOR gate will be a negation, a bar, over the A or B. You know, ordinarily, if it were to be just an OR gate without this NOT, the output will be A plus B, that is A or B. Now with the introduction of this circle, instead of it being A plus B, it will now be not A plus B, not A or B. I hope you understand that. So it can also come in this form, A or B. This is an OR gate. Then the output is A or B. Further going into a NOT gate, as I told us earlier on in class, that the NOT gate can also be represented by a triangle like this. So when A or B, that is the result of this, enters a NOT gate, it gets negated and it gives us not A or B. Then moving on to the second gate, which is the NAND gate. Yes, you guessed right, it comes from NOT AND. The N of the NOT combines with the AND to give us NAND. Now, just like the explanation I made previously, we have, for instance, 2 inputs into an AND gate. We have this AND gate, A and B. You understand that? A going into the AND gate, B going into the AND gate. What do we have? We have A and B. But we have this little friend here, the small circle, meaning whatever comes out of this AND gate gets negated by this small circle, and that is what changes it to not, that is this bar here, means not A and B. I hope you still remember that the sign for AND is multiplication sign. So we have not A and B, or you can write it like this, not A and B. There is no sign here, but it indicates that what is in between A and B is the multiplication sign, meaning AND. So also, breaking it down, we have A and B, because it's an AND gate. It gives us A and B. On entering into a NOT gate, it gives us not A and B. Now, having understood the basics for this topic, we now go into some application. Remember when we treated De Morgan's theory in class some few weeks ago? We talked about two theories which De Morgan came up with. And the first one is that when you say not A or not B, it is equal to you saying not A and B all together. And we analyzed it actually with some funny illustrations in class. You know, the pots of meat example, for those who remember. Now, we can express this in diagrammatic or schematic form by saying, or by drawing this. The signal A comes and meets this circle and changes it to not A. So what started was A, and then A came and hit this circle, and it became negated, and it became what? Not A. So eventually not A is entering into this OR gate. And then also B came and hit this circle, making it to become what? Not B. So eventually not B entered this OR gate. And then we have our output, that is not A or B. This schematic diagram, according to De Morgan, is equivalent to saying A enters AND gate, B also enters AND gate. So we have A and B, but it gets negated here and becomes not A and B. Maybe in a future video I shall be posting a kind of revision or a logical reasoning to prove this first theory, both the first and second theory. I will try to use a real-life reasoning so that we can understand the truth of this statement. So what do we have here? We have our NAND gate. So diagrammatically, we can see that a fewer number of equipments was used in executing this circuit. Both circuits are equivalent, but the most economical is this, using a NAND gate. So instead of using two NOT gates and one OR gate, making a total of 3 equipments or 3 components, why not go for one AND gate and one NOT gate to get the same result? Can you see that? And then the second De Morgan's theory states that not A and not B equals not A or B altogether. Expressing it schematically, we have A is negated here. A comes through and it's negated here before entering the AND gate. So it means that not A is entering the AND gate. And here too, not B is entering the AND gate. And it gives us not A and B. According to De Morgan's theory, this is equal to A entering the OR gate, B entering the OR gate, meaning we have A or B, but we have a NOT gate here, negating the result. So it changes from A or B to not A or B. Same thing applies here too. This is a more economical diagram to implement on your circuit. It makes use of fewer number of components, one OR gate and one NOT gate, compared to this one AND gate and two NOT gates, making 3 components, instead of 2. So I think to implement the circuit with 2 components is more economical, getting the same result than implementing it with 3 components. We have a few examples. Solve not A, or not B, or not C. From De Morgan's theory, this statement is equal to saying not A and B and C altogether. So, since it's equal to this, let's implement this statement schematically. So we have A and B and C all negated to give us an output of not A and B and C, which we have here. And if you take a look at this statement and express it schematically, you'll see that it is more preferable to implement this diagram than implementing the diagram of this. We have 2 components in this diagram, and we are going to have 1, 2, 3, 4 components in this diagram. Second example, solve not A. not A and not B. So we have not A and not B. Everything is now negated. So we read it as not A and not B. Multiplied by, or there is a AND in between these 2 brackets. Can you see that? All right. So we have not C and not D. The not covers both C and not D. So from De Morgan's theory, this statement is equivalent to not A and not B, or C and not D. If you examine it closely, you'll find out that when you have De Morgan's theory, on one side you have not, the not symbol is divided amongst the 2 entities. So you have not here, separated from another not here. If you check the previous slide, we have 3 different nots. It gives you one almighty knot covering the 3 letters. In previous examples, you can see that individual knot, this is one knot, this is another knot, it's equal to one almighty knot. Then what are you going to write under? Here you have A and B. When you have AND, it changes to OR on the other side. So Let's examine that again. We have one NOT and then another NOT. It has resulted in one almighty NOT. Then all the components that are under still maintain the way they are. NOT A is still maintained, NOT A, and NOT B. Now, what is in between these two individual NOTs? This NOT here and this NOT here. What is in between? And is in between. So, on the other side, what will AND change to? It will change to OR. It will change to OR. So, OR, then this, bring it down, C, and bring this one too down, not D. So, implementing this final answer, schematically, we have not A, that is this, not A, not B, we have this, not B, entering into an AND gate, that is AND gate, multiplication sign in between them, in between A and B. Then we have the OR sign, that means this A and B, what comes out of it will go into an OR gate. Then looking at the other side, C and not D. We have C, ordinary C, you see, this is an ordinary C. It's not negated by the small circle. So that it maintains its form, C. And, meaning it enters into an AND gate. This is an AND gate because of the multiplication sign here. Not D. This is D, and then it gets negated and changes to not D. Also enters the AND gate. So C and not D. The output comes into an OR gate because what joins this A and B and C and D together is the OR gate. That's what joins this place and this place together. So OR gate joins them together. And what do we have here? We have a negation. We have a negation at the end to negate the result of everything. That is this big brother here. That's what is at the end, to cover up everything that we have, worked for. It negates everything, and it gives you not, the almighty not of not A and not B, or C and not D. And what do we have here? We have a NOR gate here. Recognize that? All right. So that brings us to the end of today's lecture. Thank you for listening, and bye.